This is kind of a fun, quick little section. It allows us to give graphical representation to complex numbers. So because complex numbers have two parts and can be represented as a vector in the rectangular coordinate system, doing this is going to allow us to describe complex numbers in another form than rectangular, which we've been working with mostly, and that form is called polar form. With the polar form of complex numbers, we can perform two of the four operations, multiplying and dividing, much more quickly. We can also raise complex numbers to a power, and we can take square roots, cube roots, fifth roots, whatever we may need to do. This section will just look at how you can graph complex numbers in the rectangular coordinate system. So what we're going to do is we're going to represent a complex number in the complex plane. So rather than calling this the x-axis, we're going to call this the real axis. And instead of calling this the y-axis, we're going to call this the imaginary axis. So when I'm ready to graph a positive 2 plus 6j, this is just an ordered pair, 2, 6. That's all it is. It says to me, go from the origin to the right 2 in the real direction, and then go up 6 in the imaginary direction, and draw a straight line from the origin to that ordered pair. Then, if you would put an arrowhead on, and you have represented this complex number in rectangular form as a vector. We're going to, I just want you to know in the next section, we're going to drop a perpendicular here and create a right triangle, and we're going to figure out, based on this 2 and this 6, the length of this hypotenuse, and we're going to figure out this angle theta using tangent, because we were given the side opposite and we were given the side adjacent. But all we want you to do right now is to graph these. So would you go to the left 2 on the x-axis, and then would you go down 5, and would you draw a straight line? I'm going to attempt to draw a straight line. Going to the left 2 and down 5, I'm going to try to draw a straight line to the origin. Oh my, I do not know why that doesn't want to work on this particular computer. So I'm just going to have to try to draw a straight line. Done. That's the complex number drawn as a vector, and we will produce it or rewrite it in polar form in our next unit. So go ahead and practice the next one on your own. Pause if you'd like. Welcome back. I'm going to go to the right 4 and down 1. So this is where the ordered pair, this is a negative 1j. So that vector is drawn like this. Well, we've worked with vectors before. In Chapter 9, and we initially started by drawing them and adding them via a drawing. But before we do that, remember, we've already done this. If I have a real part of 4 in one of my answers, one of my complex numbers, and another real part of a negative 1, when I add those together, 4 and a negative 1 is 3. And when I add a minus 3j and a minus 2j together, that gives me a minus 5j. To do this graphically, what I need to do for this first one is I need to go to the right 4 and down 3, right there. And I am going to attempt to draw a straight line. Then I'm going to go to the left 1 and down 2 to this spot and draw a straight line. So these are the two vectors with their tails together. What we did when we first drew vectors back in Chapter 9 with their tails together, to find the resultant vector, we drew a parallel line off the head of this vector that's parallel to this other side. So we kind of, let's see here, I'm just going to look. So I'm trying to draw a dashed line that's parallel to this line over here. And then off the head of this vector, we drew a line that's parallel to this line. So I'm trying to draw a dashed line again. And then we found the resultant vector from where the tails work together to the opposite side of the parallelogram, and that was called the resultant vector. Well, what we have to do is just look at where that resultant is, and it's to the right 3 and down 5. It's to the right 3 and down 5. So via a picture, we have added these complex numbers graphically versus just doing the algebra. Now, I know it seems kind of silly. Why would you bother doing the picture when the algebra is so simple? It's because of where we're going in our next section. So would you go ahead and pause the video and draw these two vectors, tails together from the origin, and then find the resultant. Okay, the first one is to the left 3 and up 4, so I'm drawing a vector to that dot. The next vector is to the left 5 and down 1, so I'm trying to draw a line to that spot. Now I know my answer is a -3 and a -5 combines to be a -8. 4j minus 1j combines to be 3j. So my answer is way out here at x is a -8 and up 3. But I'm going to attempt to draw, I think I'll go, boy, this is hard to do on the monitor. I'm going to try to draw this one. Having trouble getting dotted lines. And then this one out there. And those were supposed to be parallel lines. This one parallel to this. This one parallel to this. And then the resultant is from the tails together to the opposite corner of the parallelogram. And that ordered pair right there should be where x is a -8 and y is a +3. You know, I'm not bad with the y is a +3. Here's 3. And this is 1, 2, 3, 4, 5. Ooh, you know what? I drew this vector wrong. It was supposed to be to the left 5, so it should have been right here. This vector right here should have been right there. Because again, it was to the left 5 and down 1. Anyway, you get the gist, I'm pretty sure. When I go to subtract, remember algebraically, when I subtract, I add the opposite of these. So this would become a +2 and a +4j. But as I were to draw this, the first one, I'd go to the right 5, 1, 2, 3, 4, 5, and then down 2. So that'd be the first vector. If the next vector was a -7 minus 4j, I'm going to draw it in green. I'm sorry, a -2 minus 4j. So -2 and a -4. This is where it would have been. However, I want to subtract that vector. So when I subtract a vector, I add the opposite. So I would have had to have gone in the opposite direction of the green line, which is to the right 2 and up 4. Again, this 5 and this 2 will add to be 7. This -2j and this 4j will add to be 2j. I know my answer should be out where x is a +7 and y is 2. I'm trying to draw a parallel line to this one. And now I'm trying to draw a parallel line to this one. And my answer would be from the tails to the opposite corner. So my answer is supposed to be out to the right 7 and up 2. So again, 7, 2. It missed the 2 by a little bit. But again, it's because it's a sketch. This one's unusual. Graph the complex number and its conjugate. Describe the relative positions. Let's just pick a complex number. Let's just pick 2 plus 3j. So 2 plus 3j, go to the right 2, up 3. So there's that complex number. Its conjugate is 2 minus 3j. So I would go to the right 2 and down 3. The conjugate always changes the sign of the y value. So this original vector, when I drew its conjugate, it reflected over the x-axis. If I folded the paper on the x-axis, I would get that line to reproduce itself down here. Let's do another one. Let's do one in the second quadrant. So a -2 plus 3j. And I'm going to erase this previous one. So if I go to the left 2 and up 3j, here's that vector. Its conjugate is, you don't change the x value, it's still a -2, but you change the sign of the y value, it's a -3j. So I go to the left 2 and down 3. And that one also reflects over the x-axis. You know, I could go on and on and on. I could write a complex number that's down here. So a -2 minus 3j. So I'd go to the left 2 and down 3. There's that vector. But its conjugate is a -2 plus 3j. j. So left 2, up 3. So a complex number and its conjugate are always reflected over the x-axis.